agenda for this lecture. As the title of the lecture today stated, it's sort of a review. So, hope you guys came with questions. Any particular lectures that you'd like me to go over? Yes?
So what's the format of the final going to be?
It's going to be a written exam, take home. It's designed to take 3 to 5 hours to take. I strongly encourage people not to spend more than, I don't know, 5, 6, 7, 8 hours on it. But you know, you could spend as much time as you want on within the time window.
So like on a problem set, there's a mix of like math.
No coding.
No coding.
Yeah. And there's no collaboration allowed on the final exam. So you cannot share ideas with anyone. It is the only thing in this class where 0 collaboration is allowed. If you have clarifying questions, of course, you can ask them beyond.
The homework that we're currently working on, training the LSTM RNNs to do, the advice that's been given on the Piazza is to run them for many epochs until they converge. What exactly is going on in this project? Like why, like I'm watching my loss at some point is kind of just oscillating now between a couple different values. It's not really dropping after like 600 something epochs. What?
600 epochs?
Yeah.
Yeah, you're probably done.
When I did it this morning after about 300, it was run overnight. And I got more words than not words, but anything less than that, like 100 epochs, was just not very tangible. So I'm just curious why does it take so many epochs to get something to do? What is happening in that? Is it just that the learning rate's super low? Or
yeah, the learning rate's super low. In general, because you're doing sequence modeling, the output space is exponential in the in the length of the sequence, and so when you in these recurrent neural nets and LSTM, they propagate gradients backwards through time, and so learning is just really slow, especially if you're doing gradient descent. On this data set, 600 epochs is probably enough. I mean, if you haven't converged to something useful, you may need to rethink the features, the architecture, or something.
Okay.
Yeah.
We've learned about a lot of different models in this class, and based on experience and what you've said in lecture, the success of a particular model really depends on the context it's applied, it seems. So I was wondering if, just kind of in the line of review lecture, if you could kind of give an overview of the different models and like different types of applications or characteristics of applications we should be thinking about for a particular model, and like essentially just kind of put them in some sort of framework.
Okay. Yeah, sure. Let's see. So there's basically, at a high level, you can think of models, first of all, are you doing supervised learning? Or are you doing a very, very straightforward supervised learning task, yes or no? Right? If yes, then that really sort of narrows the focus of the types of models you want to use. Do you want to use a linear model or a nonlinear model? If you're using, if you're using a nonlinear model, typically these days people use neural nets. Random forests are still useful sometimes. And then, did you collect the training data and things of that nature. The modeling questions get more interesting when you're not doing a very straightforward supervised learning problem. For very straightforward supervised learning problems, like your experience in the calculus competition is real life. It's like a microcosm of real life. The only thing for straightforward supervised learning that we didn't really talk about in detail is where you're getting the data from. Are you getting it from annotations? Are the target labels themselves noisily annotated? How does that impact the loss function that you choose? If you assume that the ground truth labels are good, right, then the calculus competition is literally just a microcosm of the real world. Okay? Maybe like not a competition, so you're not competing, but like the steps you've taken to train a model is basically what you see in the real world. The main challenge there is either feature engineering or figuring out if the annotations are collected are even good. And that's I would say at this point it's a pretty domain-specific issue at this point. To go to one of the biggest major tech companies, things like, if you're, for example, if you're at Facebook, is the signal that you try to predict like whether or not someone liked an article? Is it whether or not someone commented on an article? These are decisions that people in data science teams at Facebook have to deal with all the time. Right? So choosing what is the thing you want to predict. But that has nothing to do with the actual model, right, in terms of the learning model. Now, once we talk to things beyond just a straightforward supervised learning task, right? We have things like unsupervised learning, dimensionality reduction, probabilistic models, and things of that nature. The modeling question becomes a lot more interesting. So in unsupervised learning, we talked a lot about what is the right assumption that we should make in order to be able to summarize the data. And typically that assumption is, well, always that assumption is that there is some low-dimensional representation that summarizes the data. That representation could be a clustering. That representation could be like a link factor model, like those similar to SVBs. Even a hidden Markov model, right? It makes a low-dimensional assumption. It assumes that there's a small set of part of speech tags or latent states or hidden states that summarizes how the whole sequence is generated, right? In all of those, there exists this low-dimensional summary that reduces the dimensionality of just modeling and everything, sort of based on just the feature applications. Which of those is more appropriate? Sort of depends, right? It depends on what the data looks like. Does the data look like it naturally, from your inspection of the data, do you think that the data is naturally clustered? Do you think the data naturally is projected on this low-dimensional manifold? The answer to that question will dictate whether or not you choose to use a clustering-based method or a similar link factor model. What do you want to use this summary for downstream? Is it just for visualization? Is it to do something else to figure out where do you want to collect data, stuff like that, right? And then we have probabilistic models where the goal is not just to do something like a summary of the data or make a prediction, but also to compute something about probability, the probability of observers in there, or probability of a label being something. And in probabilistic models, one of the new things that you can do beyond just computing probabilities is that you can sample, right? You can actually sample data according to this generative distribution, and under the assumption that the true data set was generated under the same model class, then you've actually recovered, or you've perfectly modeled the unknown test distribution, if you can fit the parameters of the model. And that has applications these days in things like generating images, sounds, videos, things where you want to actually create new content. Now, what are some of the modeling choices one might make in probabilistic models? Well, these days, most probabilistic models is some that you see in practice are some combination of a graphical model with a deep neural net. The graphical model specifies some type of, or the structure of the graphical model specifies some type of independence assumption. If you just learn everything end to end as a single black box neural net, it's pretty much intractable because of the complexity of the output space. But the deep neural net, the deep learning part allows you to learn these highly complex nonlinear relationships between microvariables. And the graphical model or some sort of structural assumption allows you to factorize or approximately factorize the space. In the graphical model case, once you condition on some variables, you can factorize the space.
Just to follow up. So a bunch of the projects, one of the takeaways I think a lot of us have learned is that deep neural nets just work better. Certainly in the Kaggle competition, that was our experience. So barring like interpretability issues and training time, is there ever a reason not to use a deep neural net?
There's also issues with test time. Sometimes the deep neural net takes longer to run at test time. There are power issues. If you're going to run this on your phone, a giant neural net might not run well on your phone. Just in terms of raw accuracy, you're right. I mean, there's no reason to use anything else these days. Or you need a special reason, right, to use something else, right? One second. You'll need a special reason to use something else. I still often use linear models to start with, because they're simpler, they're more interpretable. It's not gonna. It's very rare that the first thing you train is the thing you commit to in production, right? So I still start with training linear models. But yeah, subject to resource constraints of a variety of flavors, deep neural nets are the default these days. Yeah. Yes?
So you briefly mentioned that sometimes you would use a random forest over a deep neural net.
That's
what
right.
would those circumstances be?
So for example, Azita Almami, she's a professor at EE here. She's working on she's working with epilepsy patients who suffer from epilepsy. So she's developing this chip that's embedded in the patient's brains, and it detects the onset of a seizure. It induces an electric stimulation that offsets that hopefully will cause the seizure to be shorter or not even arrive. Right. That device is super low power. Is running in the so the version 1 of the device you have to carry a laptop with you, right? Because the machine learning is running in your laptop. The version 2 of the device that she hopes to build, everything's on the device, right? And if you think about the structure of a decision tree, forget random forest for a second, just a decision tree, right? It's a super sparse structure, right? In a deep neural net, you have to power every neuron in the hidden layer. Then you have to power every neuron in the next hidden layer. In a decision tree, you make a branching decision, and half the decision trees you don't have to power up, right? So, I'm giving you a corner case, but it's actually incredibly relevant. Furthermore, I think it's less true these days, but even like 5 years ago, there were plenty of cases where if you tried random forest and deep neural nets, like a non-trivial fraction of the time random forests work better. I think that's less true now, but it was still true 5 years ago. There was also a time when random forests were much easier to train, but random forests are harder to model on GPUs, right? The computation, the learning algorithm. And with the recent advances in GPUs, the training of neural nets has sped up dramatically, where even though the raw computation is much more expensive in terms of running time because of how GPU learning parallelizes well, and deep learning training parallelized as well on GPUs, the actual running time is about the same. But these are all trends that I have been around the block a few times. I've been doing machine learning for 13 years. So I've seen these trends come and go, right? Like 5 years from now, things could be different. Yes.
So, the bias variance trade-off, I think I kind of understand like the general in words explanation of it, but I don't understand the equation at all.
Oh, okay, sure. That is definitely on the final exam, by the way. Okay, so here, let's see, maybe it's good to start with the previous slide. Okay, so we're trying to understand the expected test error of a model class. So F is a model. It's a model class, and F sub capital S, where capital S is a training set, is simply the function within that model class that minimizes the training error on this training set. And we can think of capital S as a random variable, right? So if we were to hypothetically repeat this process where we collect the training set from the test distribution and train a model, then repeat this process, that's a hypothetical thought experiment, and that's what this is. It's a random variable, right? And then we can say, okay, what is the expected test error of this model class for training sets of this size? And that's this quantity here, right? This is the loss of this model trained on this training set taken over the expectation of over the randomness of the training set collection process. Now in practice, of course, you don't do this, although actually you could, because the assumption is that we collected this training set is sampled IID, independently and identically distributed from the test distribution. So as a thought experiment, you could imagine what might happen if I were to do this over and over and over again.
What's P?
P is the true test distribution. So it's the loss on the test distribution, or the true distribution. And so what that boils down to then, if we were to expand all the definitions, is over the randomness of the training set, for any given example from the true distribution, compute the loss and just take the expectation over all of that. So that's the definition. So this is the quantity of interest when reasoning about the bias variance trade-off. This is the quantity of interest. And so specifically for squared error, so L was squared error, right? It turns out that what we just looked at in the previous slide, definitions up there, you can rewrite it like this, right? Where capital F of X is the average prediction, right? So, if we were to if we were to collect a training set, train a model, and then compute its prediction on this X, draw another training set, train a model on that new training set, compute the prediction of that model on this X, and just do that, to the infinite limit so that we can compute this expectation. then that's what capital F is. Right? Okay, so it turns out for squared error, the equation gets a lot more complicated for things other than squared error, but I think the equation is, for the purpose of showing this equation is just to illustrate the idea. So for squared error, you can rewrite this thing as the difference in the expected value of any individual model you would train, its deviation from the average prediction. This is the variance term. And the difference between the average prediction and the actual true target. And that's the bias term. So, if we recall, this is, well, actually I'll let you stare at this for a little bit. I mean, I could derive this if you'd like. It's not that hard. So, recall that this guy is just this minus this squared, right? That top part is this minus this squared, and this guy is this, so you just do some plus or minus some things, and then you associate them away, and then you get this. Sorry, that probably didn't make any sense. So you add a term and subtract a term, they cancel out, and then those terms end up corresponding with this guy. You apply the law of the associative property, and then you get this.
Can you do that on the board?
Yeah, sure. Let's see here. No. And now, hopefully I won't embarrass myself by having to derive this in real time. So for simplicity, I'm just going to look at one example. So I'm going to do the expected value of S. So I'm going to reverse the. Let me just write out what we had before. All right, so this is what it was before. This equals the expected value of S, expected value of X, Y sample from P, right? F of S of X minus Y squared. Now, for simplicity, I'm going to reverse this. I'm allowed to do that. They don't depend on each other. And I'm just going to drop this for brevity, right? This will apply for every X and Y pair from the true distribution. So we're just going to look at this guy. And let's just write out, and then we can just distribute this out, right? So this is F of S squared minus 2y f sub s of x plus y squared. What we want is f of s of x minus capital F of x squared plus capital F of x minus y squared. That's what we want, right? This will depend on, this has an expectation over s. Of course, since this part doesn't depend on s, we could take this out of the expectation, but we could do this. So what we want is we want this thing inside the expectation to be recomputed to be sort of equivalent to this thing inside the expectation. I'll just use s prime here just to have a different thing. And so a couple of observations. First, this is fixed. This is a fixed thing, right? There's no randomness here. It's the expectation over, over something. Let's see. So you could just reverse engineer it. That's what I do. So this part distributes to f sub x squared minus 2 f sub x capital F of x plus capital F of x squared. Just rewrite this so it fits better. So this. And this is x squared minus 2y x plus y squared. Okay, so so in order for this to match this, well, first of all, these terms can eliminate. They're common to both. And so all we need to do now is get this guy to match this guy to show that they're equivalent. Yeah? So this is equal to f of x times f of x. And that's relevant because, let me just page in the derivation of my brain 1 second. Doing this in front of like all you guys is actually a little intimidating. Let's see. So this is equal to, so right, so we can manipulate this expectation. So, right, this is actually twice, excuse me. So I'm just gonna get rid of this guy. Let's put a 2 here. And then, let's see, this y can come out of the expectation. 2y values x minus 2y, yes. So, right, so this guy, right, is equivalent to this guy. They're actually equal, right? I could, because this is literally 2y expected value of s. And expectation here, by linear of expectation, I can just move this expectation in and out. Doesn't matter. So these two things are equivalent. And the only thing now is to show that these two things negate each other. Right? And again, by linear of expectation, I can move this expectation in and out of here. So you know, there's an expectation over s outside. And by linear of expectation, I could just manipulate it until it's just exactly f of x by moving the expectation inside, and these two negate each other. And we're done. So what we did was we added and subtracted this guy. Right? These two things are equivalent. We added these 4 terms, these terms correspond to these 3 terms. We added and subtracted this guy. We rewrote this guy. We split this guy. And then we apply the associative rule and distributive rule, reverse distributive rule, and then we're done. Yes?
I have a question on the very first step you did, which was switching those expectations.
Yeah.
So on the homework, I was not sure exactly why one could do
Because
that.
they don't depend on each other.
So S is a distribution.
S is sampled from P. S is a set of n data points sampled IID from P. X, comma, Y is a single data point sampled independently from P.
Okay.
They're independent of each other, therefore you could switch around the expectations.
Okay.
Yeah.
But they're sampled from this. S is sampled from the same distribution that X and Y is sampled from.
Yes. Correct. That's the assumption. Right, so so for square, I mean, this derivation gets really complicated for things that are not squared error. But I think it's just illustrative, just as intellectual exercise to just interpret this, right? And so let me just go back to the. Okay, so right, so this is the variance term. This does not depend on y, the target label that we're trying to measure the error of our prediction of. The only thing that depends on y is this guy, which is the average predictor. Okay. So to see that in action, let's look at this example again. It's a one-dimensional data set. We're doing one-dimensional regression, right? So this is the x is 1D and the y is just a single number. And this is the test distribution, the red dots, right? And so for a linear model class, we're going to sample a training set of size 7 from this distribution and fit the best least squares linear fit to that. And the data points that we sampled are in blue, right? So that's the line we get. If we were to hypothetically repeat this process and collect another training set of size 7 from this test distribution, we might get something that looks like this, right? And so on and so forth, right? That's sort of the idea, right? That each of these is a different f sub s for f linear and capital S size 7, right? For quadratic, we get something that looks like this, right? We collect the training set of size 7, we fit the best quadratic curve that we can, and we get something that looks like that, right? This is the variability, right? And we do the same thing for cubic, right? And now, suppose we just repeated this process to its infinite limit. And here, my infinite limit was about 500, but suppose we, to create these plots, but suppose we repeated this process to its infinite limit, you get something that looks like this, right? So the black line is capital F, the average prediction, average over all the f sub s's that we trained, right? That's the black lines. And then the green line is the square deviation, I think. It's either the square deviation or the standard deviation that we just unsquared, I forget, but I think it's squared. So the green line is the square deviation is the expected square deviation of a single f sub s from the black line, right? It's the variance, right? And the bias variance trade-off says that we can actually compute the test loss. We can actually rewrite the test error as the sum of the two. The sum of the black line, which is the squared error between the black line and the ground truth red dots, and the sum of the green line, which is the squared error, which is the variance, just simply the variance of the prediction of this function class at this data point, right? And the test error is simply the sum of the two. So what this means is that when you start thinking about the model class, right? Your model class is performing poorly. Is it doing so because the bias is really bad, or is it doing so because the variance is really bad? So in this particular case, the cubic function class, and I created this data set from a cubic function plus noise, right? The cubic function class looks pretty good, right? The bias is actually really small, right? The bias is really small. But for any given training set that you might collect of size 7, you would expect the error to be quite high, right? Because the variance is so high, so large. You might get really lucky, right? And you get a model that's exactly the black line or close to the black line. But in general, you should expect to get a model that's quite different from the black line. On the linear, right, the variance is really small, right? Linear functions are pretty simple in this case, 1D regression, right? Pretty simple. But the bias is pretty bad, right? I mean, it's not really capturing some of the curvature of this training set, of this distribution of data. So in this particular case, for training sets of size 7, it turns out that the quadratic function class is the one that best balances the bias variance trade-off. Yes?
So the axis on the bias variance plots is that x value.
Yeah, it's a feature value.
Right.
We're doing 1D regression, yeah.
So that actual value of the bias depends on what x you're looking at. So in evaluating the entire model, do you take some measure, an integral? Like
It's the expectation overall.
Okay, so yeah.
Yeah, it's the expectation overall. You can look at the bias variance trade-off for a single x, y pair, and you could also look at the bias variance trade-off for the entire function class, which averages over all possible x, y pairs. Right. I did the derivation just for a single x, y pair because you just add on the expectation. On the outside, it changes nothing.
Okay.
Yes?
So if you look at these graphs, but like the green line is the variance, it looks like for data points towards your center, you're going to have like the variance appeared lower, is there any notion in general of like? if
I
you
think
can
that's an
define-
artifact of how I represented the features. Yeah.
So is there any notion in general of like if you can define a topology on your data set, like things towards the center of like of higher density?
Yeah, so you can imagine that data dependent, you could do a data dependent variance. Can you reason about where the bias variance trade-off is better or worse at different parts of the training set? So people have done that. I mean, it's not my research, I don't know the details, but yeah, you can do that. But once you do that, then what do you do next? Do you like do a separate model? Do you like, you know, the decision, downstream decision you have to make is unclear. If you're going to commit to a single model class over your entire data, then somehow you just have to live with it. Yes,
And this trade-off is independent of your choice of loss function.
so it is dependent.
It is independent.
It is dependent.
Oh, it's dependent.
Yeah, I showed this with square laws for a reason.
Okay.
Yeah.
So meaning it doesn't exist, or it's just hard to show.
Meaning the formula, I mean, I gave you a formula that gives you, that just decoupled everything.
Right.
Right? Sometimes the bias variance trade-off is not decoupled like this.
I see.
Sometimes as you increase the bias, like here the bias variance trade-off is decoupled and it only depends on your function class.
Okay.
So other times as you like increase the bias, the formula actually depends on, like there's an interaction between bias and variance.
Right, which is maybe what one would
For
expect.
0-1 loss, loss, for example, and there's a paper on this published about 10 years ago, the bias variance trade-off for 0-1 loss has a coupling between the bias and the variance. There's an interaction term. It doesn't decouple additively like this. And I cannot do the derivation of that on the board in real time. I'd have to look at the paper. Yeah.
In absence of another question.
Mm-hmm.
In some of these unsupervised learning tasks, you have certain latent variables, so PCA or hidden Markov models, and in the homeworks we've been asked to speculate or reason about the identity or what the meaning of these hidden states. So in machine learning in general, is that something that matters at all? And related to that, like a practical question, like selecting the number of hidden states or which latent variables you consider seems just like completely opaque to me right now. I don't understand how I would systematically go about understanding what to look at and why.
Right. So interpreting the latent states of the latent variables of a latent variable model, which by the way can also exist for supervised learning. You can have a latent variable model for supervised learning. I had one for basketball prediction where I showed some heat maps of where players like to shoot the ball. That was a latent variable model for supervised learning. But in general, interpreting the latent variables of a latent variable model, yes, it is something that is of interest to a lot of people. I mean, these days, as machine learning is being used more and more for lots of applications that impact us in our everyday lives, it's important to know if the learning algorithm is picking up on some really weird correlation or something that actually makes sense, right? Yeah, I can list lots of examples, and this goes beyond latent variable models, but like, you know, if your test distribution is at all different from your training distribution, right? Or if by making a prediction you actually, it results in an intervention that changes the test distribution. Right? Like for example, your Facebook, right? You train a model to sort of order the newsfeed, right? That's one of the most standard things that people do. Twitter does this, Google does this, Amazon does this, everyone does this, right? And the signal often is engagement, right, with the articles on your newsfeed, right? Okay, well, that creates a feedback loop, right? Because people will naturally just look at the top of their newsfeed, right? They might look at it more or engage more if it's interesting, and engage less if it's less interesting. But people generally just typically engage at the top of their newsfeed. It's just what people do. Like if you search on Google, you'll typically click on the top result just to see what it is. I mean, that happens often, even if it's not a very good result. And so what that means is it creates a feedback loop, right? I'm going to train, I think this result is good. I train a model, and I predict this, I'm going to rank this result number 1. It gets clicked on, so I continue to think that it's good. Right? So, it's really important to know what the model is learning, right? Because that'll create undesired behavior. That has nothing to do with what you care about overall. And interpreting latent variables in a latent variable model is just one of many ways that people want to interpret what's going on in the machine learning. With respect to selecting the dimensionality, that's a very tricky problem. You're right, there is no systematic way. Now, people often look at some notion of reconstruction error, like the likelihood of the data, as you increase the number of hidden variables. And what often is the case is that you'll see like the loss go down, the reconstruction loss go down, and then it still goes down, but it kind of flattens at some point, right? And people typically set the number of latent states to be at the point where it seems to flatten. Yes?
Elaborating on the feedback loop thing, do you think with suggestion algorithms like the weekly playlist on Spotify and stuff like that, do you not think it would, like if you listen exclusively to that like the suggestions would kind of converge towards mediocrity for everybody if you're only using
so there was actually an interesting social experiment done at Microsoft Research in New York a few years ago, where they created this like music portal, but they actually created like, I don't know the exact number, maybe 5 or 6 mirrors of it, and based off either your Facebook ID or something, when you joined the music portal, you randomly got assigned to one of them. So there were like 5 or 6 parallel universes. It was like this indie rock portal, you know, like up and coming musicians, and you know they had like a leaderboard of the most popular songs, right? And then they just let these portals evolve, and whatever became the most popular songs was unpredictable. Like the really horrible songs never made it to be popular, but of the ones who were pretty good, like there was no consistency between the different universes. Now, one should not draw too many conclusions from this because it was a very controlled and simplified experiment setting, but it does make you think. Right? So, like, do things devolve towards mediocrity? Maybe it does in some cases, maybe it doesn't in others. Yeah.
So, apart from staring at the slides, how would you suggest that we study for this exam?
Oh, I mean, I hope that through doing the homeworks, I hope this, from looking at the homeworks, and look at the solutions to the homeworks, and looking at the slides, will just be enough. So when I said 5 hours, like if you, I think that included time to go through course notes, review material as part of like working on the exam. 3 hours is where you just sort of, well, I mean, I could probably do the exam in about an hour. So that includes in the buffer time to review relevant course notes and homeworks and stuff like that. Yeah. So I don't think, like, the questions are easier than the ones on the homework typically. It's, a lot of it is actually it's conceptual. Of course, there's no collaboration allowed, right? That's the trade-off. Yeah.
Is there anything which was not really covered on the homeworks, but which we should make sure to review?
Yes.
So, going back to sort of the idea of systematically training, for the neural network, there seemed to be a lot of sort of guessing what would be ideal. So I just kind of wonder if you could tell us a little bit more of the state of the art of how you pick your parameters or optimize your training.
Actually, that's one of my biggest pet peeves about machine learning is the fact that people just spend so much time hyperparameter tuning neural nets these days.
Yeah.
I mean, there is no real systematic way. Not that I'm aware of. I mean, people have tried to use machine learning to learn the hyperparameters, right? So like if you have like a distribution of 100 learning tasks, right, or 1,000 learning tasks, can you learn what neural net architecture is good for which task, right? So there's a meta-learning step. Mixed with success, I would say, and in general, I think for most applications, it's actually not worth it, right? For most applications, the difference between 95% accuracy and 96% accuracy, like if one's trying to win a Kaggle competition, like it's just not worth it, right? Like the cost-benefit trade-off is not there, right? Because you have this whole system you're trying to build. Like assuming you're part of a company, part of the engineering team, building out a product, like the cost-benefit trade-off of like tweaking your neural net to death is just not worth it because it's part of a larger system, right? Times where it is worth it, like for example, Google, they can predict whether or not you'll do better ad placement, right? That's worth billions of dollars for them, even for a 1% improvement, right? But for the majority of the use cases, it's just not worth it. Just like train a model, make sure you're not overfitting, do some cross-validation, hit some benchmark that you think is good enough for this whole system, and just leave it and come back to it later if this product you've built turned out to be like insanely popular, where increasing the accuracy of the neural net by 5% is worth however much, X amount of money. That would be my recommendation. Yes?
Do you think we will see like a future movement towards more systematic, rigorous approaches to...
I mean, you sort of already see that now in the sense that there's sort of like a few set of prototypical architectures that people use. And what many people would just sort of try those and then just pick the best one. Now, that's not, maybe that's not systematic in the way you're thinking about it, but it's sort of like somehow through the wisdom of the crowd, these are the 10 architectures that people tend to try. And if you have a certain cost-benefit trade-off, like I just want to pick one that works pretty well with a minimum amount of time invested, then that's not an unreasonable place to start. In terms of, something a little bit more scientifically rigorous or mathematically rigorous, yeah, I think there's hope. There's some interesting new learning theory results that came out in the last year and a half that are kind of interesting. But I think the jury's still out. Yep.
So beyond your special topics course next term, what do you think are the most valuable machine learning courses for relevant problems here at Caltech?
Well, I don't know what class Anima is going to teach next year. But whatever it is, it's going to be a good one. I suspect it'll be an optimization for machine learning. I don't know, but whatever she teaches will be a good one. You know, one of the drawbacks of Caltech, due to its size, is that we don't have good course coverage compared to other universities. I honestly think that at some point taking courses is a crutch. Like I think that the courses are designed to introduce you to an area so that you can learn on your own. You know, so I honestly think at some point taking courses is a crutch, with the perhaps sole exception of very, very mathematically abstract courses. There you could maybe extract a lot of value from taking a lot of courses. But for these types of courses, like if you, you know, there's like 100 or so online courses in machine learning. You took one, you've taken them all. So whatever advanced topics class that Anima teaches will probably be cool. But at some point, the point is so that you can learn on your own. Because if you're always taking courses, it's actually a very inefficient way to learn, right? Because you're learning a bunch of stuff that you're not going to use, right? The purpose of a course is to get you comfortable enough in an area so that in the future, if there's something you need to learn quickly, you have the confidence and the ability to just find the resource to teach yourself. If you always have to take a course to learn about this one thing that you need to do for some other project, I mean, you'll spend your life taking courses. So I think taking courses is actually, in the long run, super inefficient, but it's necessary to get you started. Yes.
On your lecture on regularization, you showed an equivalence between regularized least squares and norm constrained model. I was wondering if you could review that derivation.
What was the question again? It was
equivalence between a norm constrained model and L2 regularized least squares.
Right. Right. So, you know, this is sort of the de facto way that we do learning these days with L2 regularization. And, you know, when we talked about, at least in the beginning of the class, when we talked about model classes, right? I mean, we're not learning over a model class here. So how is it that we're learning more or less complex models? That was the starting point of this part of the lecture. And so in order to understand how this learning objective relates to learning a more complex or less complex model from the perspective of model classes, one needs to look at the dual, if you will, of that problem, which is norm-constrained model classes, right? So if we look at all linear, so here it's visualized in 2D. If you look at all models of norm at most 1, then you get everything inside the red circle. If you look at all models with norm at most 2, you get everything inside the green circle. If you look at all models with norm at most 3, you get everything inside the blue circle. And now here clearly, you have a hierarchy of complexity in the model class because everything in the red circle is included in the green circle, and everything in red and green circles are included in the blue circle. So the blue circle is necessarily, by definition, more complex, right? So, and the way that you would sort of write that out mathematically is something like this, right? You want to train a model. You want to parameterize in the model and minimize the loss, such that the 2 norm or the square of the 2 norm is less than some constant c. And if you actually plot the L2 norm of your weight vector, right, as a function of lambda, for solving this problem, you will always get a monotonic relationship. Yeah? At least for linear models, you always get a monotonic relationship. And so that suggests that there is a relationship between some notion of complexity hidden inside this conventional learning problem and this interpretation of complexity from the perspective of model classes. And that relationship is realized through Lagrange multipliers. And so if you think of the blue heat map as the loss function, right, where the darker part is the minimizer, right? Then if we're at that, if our model is at that yellow point, then the gradient just points towards the minimizer, right? So this is unconstrained. Once we add this norm constraint, right? If we're inside the boundary of the model class, nothing changes. If we're at the boundary of the model class, well, we can't actually leave the model class, so we somehow project back onto the boundary, right? And at some point, if we walk along the boundary, we'll get to a point where the gradient pointing towards the minimizer is exactly the same direction as the tangent normal of the boundary of the model class. And what that means is that if you do a projection, you project back on the exact same point. Right? You're done updating your model class. You will never leave this point. Okay. So an optimality condition of this norm constraint optimization, right? You're optimizing, if you're trying to minimize loss subject to this constraint on your model class, is that the gradients are aligned. The gradient of the tangent normal of your boundary of your model class and the gradient of the loss function. Now, we're doing gradient descent, so just one minor detail is that they're actually aligned with a negative sign, right? For some non-negative coefficient lambda. Okay, so that is the norm constrained model class, right? And this is the optimality condition, right? At optimality, this property is satisfied. Right. We can write out the Lagrangian if you've taken multivariable calculus, which I believe everyone in this class has taken. You can write out the Lagrangian. And the claim is that solving Lagrangian is equivalent to solving the norm constrained model class, right? And so if you take the gradient with respect to W of the Lagrangian, and you set it to 0, you get back that this has to equal this, right? And that satisfies the first condition. And then if you take the gradient with respect to lambda, it's a little bit more complicated, but it satisfies the second condition that the norm has to be norm constrained. So now, we look at these two different types of learning problems. Well, we learn minimize loss subject to a norm constraint in the model class, which is the standard way we think about model classes, right? Plus this sort of L2 regularized learning where there's no seeming notion of a model class, but somehow we're claiming that this is a trade-off between model complexity and error, right? Minimizing error. And it turns out that if you hold lambda fixed, right? If you hold lambda fixed, then it's equivalent to solving norm constraint for some c. Right, so for every choice of lambda in the sort of conventional learning problem, there exists some c for which we are solving the norm constraint monoclass train. And that's the relationship.
So the empirical relationship you showed between the LT norm and lambda, does that come somewhere out of these derivations, or is that just an observation? Like what?
Yeah, it's true for linear functions. Okay, it's monotonic. The relationship is monotonic.
Okay.
For like deep neural nets, it might not hold because of non-convexity and other issues. You know. But for linear functions, it's true. Yes.
It was only ever mentioned in passing, but could you comment on L0 regularization and when you might be able to use that? Or
Right,
how
so you
might
can
use
never
it?
use it, is the answer. It's flat or discontinuous everywhere. Because it counts the number of Manzur entries, so that's a flat or discontinuous function.
Okay, so we have to try every value.
Yeah, it's not actually even a norm, like under the mathematical definition of what a norm is. If you want sparsity, you use L1 typically. All right, I think that's it. Good luck on the final.